Hi everybody, we're getting back to work with section 3.2. Um, I wanted to take a little side trip here um, to just illustrate exactly how important the idea of relation and function has been uh, to the modern world. Um, the, there's this thing called relational databases. They did not exist even though computers were essentially pioneered at the end of World War II. They were developed during the 1950s and put into commercial production in the late 50s and 1960s. People tried storing data in them with limited memory and limited software design. It was very inefficient and very error prone. Um, the the big breakthrough came when a gentleman named Codd, who worked at IBM, published this paper. Notice its relational model for essentially large, what we would now call databases. They called them data banks back then. You deposited your data in the bank. You can find the reprint on the web. It's a very important historical document for computer science. And the entire idea, he used the word relation exactly as we use the word relation. It was a way of keeping information together. You could keep an X and a Y and a Z and a W. You could keep hundreds of variables together in one related group. The idea was that you would use a function to connect these things. Um, Typically, what you ended up with, the function related the keys, because functions, each input can have exactly one output. That meant that you could always trace through the keys to find exactly one thing. Um, this one revolutionary idea has made most of what we call the information revolution possible. If you do uh, uh, a search with Google or any other search engine, you are essentially returning what we call a search set or a query set from a large database. All Google does is crawl through the web and try to reduce everything that looks interesting into a database form with what they call an index so that they can quickly search it. Um, this idea was so fantastic. Well, it was so fantastic that after about 7 years, this gentleman named Larry Ellison and his partners realized that IBM wasn't using it. And they um, they mention inspired by a technical article in an IBM journal. Notice that they're rather reluctant to actually give Codd credit for his idea. They want to they've been very eager to maintain their proprietary claim to everything in this database. Um, they pick up a contract with the CIA, and they're going to build a special database. You've heard in the news that the NSA has been building a database of U.S. phone numbers, license plates, um, and emails. Well, they were doing it back then. Um, they codenamed that database Oracle. Um, and um, Ellison's company manages to finish they contracted to work for 2 years for the CIA. They got it done ahead of schedule, and they had a remaining year to develop a relational database management system for the commercial market. This, they simply took the CIA code name and turned it into the name of their company. This is one of the biggest software companies in existence, and they actually predate Microsoft. Um, you may have heard in the news that Larry Ellison's uh, uh, racing yacht finally did win the World Cup. He's been after that for a long time. He's an incredibly competitive guy, and he is one of the richest people on the planet, according to Forbes magazine, principally because this idea of relational databases was so fantastic. Um, our very own banner is built on Oracle. Uh, so um, this stuff, this stuff is the 21st century. The idea of function and relations only been around since as we know it now, since the late 1800s. It's a fairly new idea in mathematics. So the graph of a function. The graph of a function, that's really the picture of the function in the Cartesian plane. So the way that works is that for a point, you have an x coordinate. So say x is there. To graph a point in the plane, you need to have a y. And we get the y for the point by using x as the input to the function f. So that's why we often say y equals f of x. That's really defining the graph of the function, or defining, this is saying the output of the function is this. These are two different ways of saying the output of the function. In fact, if you're defining the function that way, both of those mean output. So here's a quick warm-up example. Determine the domain and range of each relation. Remember, a relation has a domain and a range. And then determine whether your relation might be a function. So we'll take a look at the relation in part A. Well, first off, if we call this relation R, then the domain of R, remember that that's our abbreviation for domain. I'll write it over here in the margin. I like to tell my students that mathematicians are inherently lazy. We write as little as possible as long as we don't lose any information. So domain of R, that pretty much tells us what we need to know. Now, it's going to be a finite set. We'll see here in a second that it's going to have 4 elements. And so I'm going to use set braces. I was fiddling there trying to get the focus to work a little bit better. And the domain is the set of all x values in the relation. So I've underlined the x values there. So the domain would have a -3, it would have a 3, it would have a -2, and a 2. Now, sets only care about membership. In fact, that's the most important thing about a set. Can you decide the membership? In fact, that's a good definition mathematically for set. It's a mathematical object for which membership can be decided unambiguously. So we don't really care about the order. Sometimes when we're trying to be polite, we list the elements in ascending order. There's no requirement. Each of these is correct. Do watch out though, because my math lab sometimes gets picky, and my math lab might only take the second one. On a test, these are both correct, so either one would be acceptable. And there are several other that you could, several other arrangements that would be fine also. The range. That's going to be the set of all, well, that's a really crummy curly brace there. That's going to be the set of all y values. Well, there's a 2, there's a 2, there's a 3, there's a 3. Now, that means there are only 2 of these things. Repeats don't matter. If 2 is a member of the set, writing it down twice doesn't make it any more of a member. So it would be silly and essentially it would indicate that you don't know what a set is, so I'm not going to write down 2 twice. Likewise, there's 3 twice. So the range is only these 2 points. In this function, you're only going to see 2 possible outputs, a 2 and a 3. Now we ask, is it a function? To be a function, the x's can only occur once. -3 only occurs once as an x. 3 only occurs once as an x. -2 only once as an x, and 2 only once as an x. So the x values are unique. That means they appear once. Therefore, this is a function. Now, the fact that y's appear multiple times is not a problem. The function can get up to the same height multiple times, but you simply can't fail the vertical line test. We'll see later on this semester there is a horizontal line test, but that's for a different property of a function that already exists. If we look down here on part B, let's call this relation W. So the domain of W, that's going to be a -3, a 3, a -2, -2. We see -2 being repeated. So that means in a few seconds we're going to be writing down that this thing is not a function. So that was a problem if we wanted it to be a function. If we're being a referee, we simply call them as we see them. It's not our problem. The range is going to be a 2, a -2, and a 3, and a -3. And with duplicated x's, we're not a function. And that's because if we graph this relation, you'll see us failing the vertical line test in just a few seconds. One, 2, -3, 2. 3, -2. -2, 3. -2, -3. So this relation is just 4 dots in the plane. It's 4 points. There's not a line segment anywhere in this. But even with 4 dots, we manage in one place to fail the vertical line test. So this is not a function. We could see that when we saw the 2 x's duplicated. This was coming down the pike. Here's a function that's already graphed for us. And we can immediately see that this is not a function because there's one place where it fails the vertical line test. So we may as well dispense with that question now. So fails vertical line test. Therefore, not a function. That means it's just a plain old relation. So we can talk about its domain. The relation, let's give it a name. Let's see, Q. So I guess you can guess what I'm thinking about right now. The domain will be all the x's. Well, you can find the x's by just dropping down to the x-axis. There will be a -3, there will be a -1, there will be a 0, and there will be a 1. So just drop vertically down or up, if the case were true, to the x-axis and see what your x's are. Now notice that we don't have an interval here. We don't have anything between -3 and 1, just those 2 points. So we're listing that finite number of points as a set. Likewise, the range of Q, move horizontally to the y-axis. From here I can move over and I can get a 1, but I would get the same 1 from either of these other 2 points on the left. I can get a y value of 2 here or a y value of 2 here, so I see y values of 2. And in fact, the range of this function is exactly the set containing 1 and 2.